In this video, I will talk about a distribution that is new to us called student's t-distribution. We know from the central limit theorem that the sample mean has a distribution with mean mu and a standard deviation of sigma divided by the square root of n. Therefore, if we want to compute the margin of error for a mean, the formula would be the critical value times sigma divided by the square root of n. Now we have a problem. We would only want to build a confidence interval when we don't know the population mean. But if we don't know the population mean, how do we know sigma, the population standard deviation? I'm going to say that again because it's an important point. It would be really strange to know the population standard deviation, that's sigma, when we don't know the population mean. We could use the sample standard deviation to estimate the population standard deviation. However, estimating the standard deviation from the sample gives us another source of uncertainty. William Gossett first published information about this distribution in 1908. Gossett worked at the Guinness Brewery in Dublin, Ireland, and worked with very small samples while testing raw ingredients. Guinness didn't want Gossett to publish the papers, intellectual property and all of that, so Gossett published under the pseudonym Student, and at first this distribution that he wrote about was called Student's distribution. Another famous statistician, Ronald Fisher, started using the letter T for this distribution, and it's now called Student's t-distribution, or sometimes just the t-distribution. Notice that the formula for this t-distribution looks a bit like a z-score. The sample mean minus mu divided by sigma divided by the square root of n would have a standard normal distribution. But now we're estimating sigma with this sample standard deviation, s, and that changes the distribution. We no longer have a standard normal distribution. So what does this new distribution look like? In some ways, it's similar to a standard normal distribution because it's bell-shaped, symmetric, and the mean is 0. However, both the shape of the density curve and the standard deviation change with the sample size. For small samples, the density curve has thick tails. As the sample size increases, the curve gets closer to the standard normal distribution, and the standard deviation gets closer to 1, though the standard deviation will always be greater than 1. Let's look at some graphs. The darkest line is from the smallest sample size. You will notice that the tails are thicker, and it's shorter in the center because we still need the area under the curve to be equal to 1. The lightest line, a pink line, is the standard normal curve. You can see that as the sample size increases, the center gets taller and the tails get thinner. And a definition: degrees of freedom. Officially, degrees of freedom is the number of independent values that we have to use to make an estimate in a statistical distribution. Right now, that definition might not make a lot of sense, but the most important thing to remember is that for a t-distribution, the formula for degrees of freedom is n minus 1. Why do we care about degrees of freedom? Because the density curve changes with the sample size, so we need the sample size to find probabilities. However, the tables and a lot of calculator functions ask us for degrees of freedom instead of the sample size. Why, you might ask? Why can't they just ask us for the sample size? That is an excellent question, and I don't know the answer. The people who print the tables and the people who design the calculator functions didn't ask me first. In class, we will practice finding probabilities for the t-distribution, and we'll discuss a little bit why degrees of freedom is equal to n minus 1.